Okay, so before we talk about the dimensionless parameter, we talk about the Gaussian equation property. And this Gaussian equation, the mass, momentum, and the energy equation, basically they are system equations. That means they need to satisfy at the same time for the same problem. So at the same time, three equations must be satisfied. So usually this is mentioned as a system equation. But basically this is a Laminar case. In your research, I think most of your research are doing the turbulent problem. So turbulent we come out additional parameter. Okay? So this maybe will be more simple than your research problem. Because for Laminar, this velocity and temperature, pressure, they are the constant. They don't change with time. But in the turbulent, there will be fluctuation. So you need to consider the fluctuation value in the turbulent case. Okay? So for this problem, we have three, but the velocity is a vector parameter, just like we mentioned before. Also, this kind of equation, complete equation, they have some nonlinearity. Usually this nonlinearity, anyone have an idea where they get the nonlinearity? Usually it's in a convection term. Usually in the convection term, for example, for the momentum equation, we have a velocity and the velocity gradient. If you are in the temperature, in the energy equation, you have a velocity with a temperature gradient. But both velocity and the gradient are unknown. So this is the problem in the equation, in the Gaussian equation. Usually, this is the problem. Okay, so for this problem, the simple way is we make that become two linear equation. So that means in some of the case we will reduce the nonlinearity. So reduce the nonlinearity, that means you need to have some assumption. Okay? So there must be some reasonable assumption. You can use the linear equation. Otherwise, you must consider the nonlinear effect. Later on, we will talk about when we can use the linear assumption. And for this part, we are kind of review the partial differential equation. In the fluid dynamics, there are several equations we need to consider the partial differential equation because you have space in a different direction, even in the steady flow. And if you are in the transient flow, of course, you must be the partial differential equation because you have an additional time, the differential term. Okay? So if we, even in a steady state, this is a common partial differential for the second order equation. The second order equation does mean the maximum differential is second derivation. And for the second derivation, that means the A, B, C, D. they can be the function or constant for the x, y, or the unknown function. Phi is some unknown function we're going to solve, and this phi usually is a function of x and y, or most of the simple case is they are constant. So they are classified as elliptical, parabolic, or hyperbolic, depend on their coefficient. So we have some very common equation. For example, like the Laplace equation. This is in our momentum equation. In the momentum equation, viscosity term basically is a Laplacian equation, okay? And the energy equation, in certain of the case, we can come to the heat conduction equation. So energy equation, sometimes we will have this kind of heat conduction case. The wave equation, I think in this class we don't talk, but usually if you have some kind of fluctuation service, or you like to go to surf, not exercise, okay? Then you will consider this wave equation, the wave, how to move it, and how they relate to the flow motion. Because you see the wave, the water particle motion is a wave. Do you know the question? You see the wave go up and down, right? Does water particle go as this way, or is a wave? You think it's not?
No.
Okay, you think yes? Okay, so what kind of motion they are doing for the water particle?
Vertical.
I think it's relevant that they still have some arranging.
Okay, I think this is maybe it's not in this class, but basically the full particle will go circular. So you can see a wave go one, then the water particle is go like a circular. Then they transfer this energy to the neighborhood of a water particle. So usually when talk about wave, I will tell the student when you go to the baseball stadium, people do the human wave, right? You see a human wave, and you see the wave going, but these people just stay original location. They transfer energy, but they don't motion. So one is like the motion, one is like the energy convert. You can convert energy to the neighborhood, but you don't need to move. Okay? If you move and carry the energy, usually it's a convection. Okay? But if you just transfer the energy, conduction and the wave is like this. They transfer the energy. Okay? So from here you can see for the Laplacian, that should belong to the elliptical. Okay, so different kind of category usually they belong to the boundary condition or belong to the initial condition. For example, like the heat conduction equation, this belong to either initial condition and boundary condition because both conditions will determine the final result. Okay, so different kind of category will depend on what kind of boundary condition or initial condition make their solution difference. So the first dimensionless parameter, we introduce the Prandtl number, and for the Prandtl number, what kind of a concept we're going to talk about? Anyone have an idea?
Heat transfer.
Heat transfer. Prandtl number, later on we will see the Prandtl number. So one is for the heat diffusion. This is for heat diffusion coefficient. And heat diffusion coefficient, later on you will see in this equation from the energy equation. Another one is from the momentum equation. Later on we will show this mu correspond to the density and the dynamic viscosity. And the two diffusion parameter, we want to compare boundary layer. One momentum boundary layer, another thermal boundary layer. So Prandtl number, basically, we want to talk about the boundary layer. The reason I talk about this because the boundary layer is the concept proposed by Prandtl. Okay, so probably you need to connect this together. Right now, there is a textbook. It's the boundary layer. I think this book is published in the last century, like 1970 or 1980 around. Even right now, 21st century, people still use this book because this book was edited by one of Prandtl's students. So right now, they still have many Prandtl student has influence in this fluid dynamics field. Okay, so because if you talk about boundary layer, you must mention Prandtl, and he's one of very influenced fluid dynamics in the last century. He also has a very famous student. It's called von Karman. Von Karman is one of his students, and von Karman has a significant contribution to the aerodynamics. So that's related to the airplane design. So although Prandtl didn't serve in the military service, but he gets some kind of, I think it's some label in the military, because he has a lot of contribution in the Air Force. So I think his level in the military is quite high. It's not general, but less like a general. Okay? Okay, then we take a break. Then later we talk about this first dimensionless parameter.